Hello everyone, welcome to my channel. In this video, we're going to take a deep dive into how small language models, SLMs, can be fine-tuned to solve text-to-SQL effectively and in many cases better than the large language models. Now, text-to-SQL is a task of converting natural language questions into SQL queries. In simple terms, it allows the users to ask questions in plain English and get answers directly from the database. This capability enables business users, analysts, and decision makers to derive insights from the data without them writing the SQL query by themselves. Today, most common solution relies on large frontier models, typically using a RAG-based approach, where a database schema or a subset of the schema is injected as context, and the model generates the SQL using its pre-trained capabilities from the user's query. But as the adoption grows, this approach is starting to show some serious cracks. It's expensive, it's slow, and worst of all, it's unreliable in production setups. So in this video, I'll show you how text-to-SQL becomes a heavyweight problem with large language models and how execution-aware reinforcement learning on SLMs offers a cleaner, cheaper, and a more scalable alternative. Now let's start by understanding why this problem becomes so heavy in practice. And there are four major challenges that show up consistently in real-world deployments and what we have learned by working with customers around the same problem. First is the cost. Now, assume you're using GPT 5.1 and you receive 10,000 calls per day. So that roughly sums up to around $85 per month. Now, as the system scales, and the things will add up very quickly and the cost grow linearly. So it could be that the number of calls per day has increased or the number of users have increased. So the cost for that LLM grows linearly depending on whether it has the calls or the number of users that have increased. Additionally, you may pay the same amount for the same query, even if the underlying SQL schema doesn't change for months. You might argue that I can actually cast a query. However, identifying if to rightly identify a match using the current query or a previously generated SQL or a previous user's query is not so reliable in practice. The second problem is the latency. Now, we all know the large language models have way too many, in fact, billions of parameters, and they have to do way too many calculations for the simplest conversion of a natural language text to a SQL query. Hence, they generate tokens very slowly. That delay directly impacts user experience, especially for interactive analytics where users expect near instant responses. Now, remember, the users may not just look for the data. They're actually looking for the insights derived from the data retrieved from after firing the SQL successfully on the underlying data store. The third is the hallucinations. Now, big models often invent columns, tables, or joins that simply doesn't exist in your database. Now, this problem is especially pronounced in RAG-based setups where the schema context is injected dynamically, but still the model guesses beyond the reality. The final and the most dangerous of the problem is the SQL fidelity problem. In this case, in this type of failure mode, the SQL looks correct, it parses correctly, but when you execute it on the underlying data store, it fails because the logic doesn't actually align with how the database engine works. Now, there's no partial credit here. It either runs or fails completely in production. So these are the four issues: cost, latency, hallucination, and SQL fidelity that make the usage of the large language models for the text to SQL problem a heavyweight solution. So what's the alternative? This is where small language models come in. Models like Qwen, Phi, or any small language model are extremely fast. They are lightweight, cost efficient, and can run on any T4 or 16 GB GPU machines. Now, from an infrastructure and latency standpoint, this is exactly what we want. But there's a catch. Out-of-the-box models lack reasoning depth. They struggle with complex schemas, they break down the multiple table joins, and they don't understand execution constraints. So SLMs give us the speed and efficiency, but not the correctness, at least not without the right training strategy. The obvious reaction is let's fine tune the model. And this is where many teams fall into a trap. Traditional supervised fine-tuning or SFT teaches what I call the parrot effect. The model learns very well what SQL looks like, but it doesn't know or learn how the SQL actually works. Now, it memorizes the patterns during the training period, it reproduces the syntax very well, but it has no understanding of the execution semantics. Now, this leads to a second issue, brittleness. Now, SFT forces the model to memorize training schemas. The moment you deploy it against an unseen schema, it breaks. And the reason behind it is because there's no real generalization happening. And this leads to a crucial perspective shift. Text to SQL is not a translation task. This is not English to French translation. Text to SQL is a behavioral execution task. SQL in this case is binary. It either executes successfully or it throws an error. There's no partial credit. Now, once you see the problem this way, it becomes very clear that supervised fine-tuning alone leads to a fundamental misalignment. To perform behavioral modification of the SLM so that they align more to the schema, they align more to the syntax, they make sure that the execution happens accurately, we need to try a different approach. And in this case, it could be reinforcement learning. Reinforcement learning techniques are historically proven to be costly in terms of infrastructure and overhead to create curated datasets. So how do we train an SLM to reason about the execution without introducing massive infrastructure overhead or human effort in data preparation? Now, this is where Group Relative Policy Optimization or GRPO helps. The GRPO simplifies the traditional RL training by introducing two key changes. One, there is no critic model. Two, it replaces the reward model with a reward function. And here's how it works, and I want to explain without any fancy math equations. For every input, the model generates multiple candidate SQL outputs using the same policy or called the baseline policy. In this case, as you can see, we're generating 4 SQLs for a single input. And then we use the reward function to score them independently. At the same time, we also compare each output relative to each other. The relative advantage, that is how good the outcome is compared to an average outcome. In other words, also called as normalized relative advantage. You think of it like you're trying to get an average of all the reward functions and trying to find out how good each candidate's output is compared to an average output. And this particular, the output from the advantage function is what determines what a policy update is. And if you're new to RL, policy update is nothing but how much the model should change to create a better output next time. This whole all these steps from the candidate generation till the advantage creation, advantage comparison are the actual job of a critic model in a traditional training loop. Now we're missing an important point here. How do we know if the candidate output is good or bad? The key here is the reward design itself. We ground the model's output in reality using a reward function, or also called as rule-based rewards instead of a reward model. In our case, the reward function is a combination of 4 weighted signals. So for every candidate SQL that is generated, we calculate the following rewards. The first reward is called the SQL fence reward. This ensures the output is valid and contains SQL. In other words, it doesn't contain text or code in any like kind of Python language or in any other language that the model generated to solve the user's query, because we are only looking for a SQL output. The second is the format reward. This ensures the SQL parses fine. Here we can use tools like SQL plot to walk through the AST and penalize malformed SQL queries. The third is the SQL fidelity, spread across actually 2 different functions. First is determines how many columns used in the SQL query actually belong to the table. The second tells if the SQL that is actually generated can execute fine on the underlying data store. In addition to all this, we also penalize the model for not producing a SQL at all, so that if the model fails to produce a query at all, it receives a -1 penalty. This way, we are forcing the model to always attempt execution and learn from the failure. Each of these reward functions are in fact weighted. The weights act as hyperparameters that can be fine-tuned during the training process based on the behavior of the model. Now, at this point, the model is no longer guessing what SQL looks like, but it's also learning what actually runs. Now, with this context, let's look into how the experiment is set up. Now, if you want to quickly understand everything end to end, I recommend going through this notebook, which I'll put it in the comment section. So this notebook does an application experiment for some SQL schemas, and you will be able to understand the training, evaluation, and the data processing stage end to end by going through this particular notebook. Now, coming to the full training, I want to split this into 3 sections. The first is the data preparation stage. Now, in the data preparation stage, we have 10 key steps. The first is we download the data sets from the corresponding global, the publicly available URLs, and then we extract the databases. Now, both Bird and the Spider databases come with their own respective format of the SQL schemas and the actual SQLite files. So we have to extract those independently depending on their current the structure of how they are zipped together, and then we serialize the schema and the table definition so that we get a single unified data frame of the SQL and the database and the corresponding schema. And then we load the serialized schema, we load the examples into the data frame, we match the data, the example SQL queries, candidate SQLs, and the actual user queries against the database schema. And then we merge the Spider and the Word databases together. Here we perform a stratified split, and this is a very important step. So whenever when you're training the model, you have to be very sure that the the train and the validation samples only contain the schemas that are not seen by the test sample, right? So we are using stratified split to ensure that the if I'm taking 10 databases, the 10 databases split according to the training percentage and the validation percentage and also the test percentage, but they are all independent schemas. And then we build the prompt datasets, and we basically generate a prompt using the SQL user query and the system prompt, and then we save those splits using the test string and the validation datasets. Now, at the end of this whole exercise, you will see two important things. One is that you'll be able to see that you have a trained CSV. The trained CSV is having the following aspects. One is the prompt that we're going to run on the model. This contains that the general system prompt followed by the user's query and the schema. The solution here is the expected SQL. The schema is what we have sent to the model as a context, and the source database. The source data. This is the data source basically, whether it's a spider data set or a bird data set. And the last one is the column, is the table name. Similarly, we have the validation data set and we also have the test data set. The second important output of this exercise, when you run this on the AML cluster, is basically you get a folder structure like this, wherein the SQLite files are stored for every database. So if you can see here, this is the California Schools SQLite, and you'll also see the SQLite file for the card games. And later I'll tell you why this is required. This is very important in calculating one of the reward, which is called the execution reward. Let's start by understanding the training phase. And before we move into the training phase, there are three configurations that are important to understand. The first is what is the model I'm going to use here. It's Ansloth Quen 2.53 billion model, and I'm loading it using bfloat as a data type, and this is of course hardware dependent, so you have to choose the corresponding hardware to make sure this bfloat data type is supported. I'm loading it in 4-bit, and I'm using the Ansloth gradient checkpointing. The LoRa rank is of 32, and this is doing the inference, and the memory utilization I'm keeping it at 0.6. The other important configurations are basically that how many generations you want to do for each candidate prompt. You can increase this if you want to get a better estimate of the advantage. And you have the max completion length. So we'll have to do some engineering data EDA to identify what is the maximum SQL length that you want to let the model generate. So, like for example, some of the databases in Bird or in Spider has 130 columns. So you either choose to keep it or you can exclude the database. But if you're choosing it, you have to make sure the SQL completion length is matching the largest SQL that can be produced. The temperature setting is understandable. I'll come back to the beta in some time. This basically defines the KL penalty, the hyperparameter for the KL penalty, and how many updates you're doing. And ablation is basically whether I'm running an ablation experiment or a full experiment. The second important configuration is the reward. Like I said, there's a format reward, weightage to the format reward, weightage to the execution, whether it's executes fine or not. This is an important reward function, so I have provided more weightage to whether it executes fine or not. And then you have the SQL fidelity reward and the SQL fence reward. There is no SQL penalty reward. We're going to penalize the model if the model doesn't even generate a SQL. And this penalty I've not spoken earlier, but this penalty is basically if everything executes fine, but it references unknown schema, and it's failed because of generating unknown schema which doesn't even exist in the context. So that's the reason we want to further penalize the model for generating something that references unknown schema items. The last is the training arguments. Where do you want to put where do you want to save the checkpoints? How many? What is the training batch size? And what is the evaluation batch size? So the Ansloth follows a particular math formula for identifying the per device train batch size. So you'll have to make sure this formula is always is applied when you're changing the batch size, or if you're changing the number of generations. It has to be divisible. This particular the multiplication has to be divisible by the number of generations. So in case you're going back and changing the number of generations, make sure that this particular product is divisible by the number of generations. So we have the learning rate. I'm using a cosine LR schedule, learning rate schedule, so that you have a spike in the learning rate at the beginning, and then gradually it comes down. I'm only training for 5 epochs. It usually takes 5 to 6 hours for 5 epochs, but if you want to train, you have more hardware capacity or the GPUs, you can go for higher epochs as well. The rest are pretty common. I'm using an Adam 8-bit optimizer. You can also switch the optimizer if you can try using a different optimizer and see whether it produces better rewards. Now coming to the train of the trainer function. So there are three important steps: is whether we load all the training data and the reward configuration, and then we determine whether what should the model data. This is more hardware specific in a sense. Depending on your runtime profile, you either choose the B float or float. So if you're running on V100 or whether you're running on a different GPU system, it basically resolves the model's data type. Fast inference, of course, is also dependent on certain factors, what is your CUDA version and all of that. So I'm using a helper to determine based on the underlying hardware what should be the fast inference, the configuration for the fast inference. The important aspect is that now we are downloading the base model from the from the Unsloth library, and then we are setting the parameters from our training configuration, which I showed earlier. And then I'm applying the PEF configuration. Here I'm using LoRa rank 32, and I'm only targeting these four models, which is QKV and the output, the projection, the last layer of the language model. You could also do more modules. Again, it depends on your hardware capacity, more hardware capacity and the appetite to run the training. But in more production setups, if you want to do a more standardized, get you have a much more complex databases. I would recommend to do multiple experiments using like more layers depending on how your outcome is. When you start small, you have few modules at the beginning, and then you can introduce more layers if you see that it's not the rewards are not getting flattened. And then we basically go apply the GRPO configuration and then start the train. Now, once the training is completed, I'm saving the LoRa weights. I'm not saving the actual models. You only have to save the LoRa weights, and then that's the end of the training. And let's see how the training outcome is. So after 5 hours of training this model, you'll see that the rewards. So this is the learning rate. So at the beginning, the learning rate spikes to this sees a very high spike of the learning rate. It increases rapidly and then gradually decreases to a bare minimum. The important aspect here is how the reward. So this each point that you see here, each reward you see here is a combination of the for every input and for every output, we calculate the reward using the reward weight matrix that we have seen, and then we combine all of those to get a single number. And in the beginning, you see that reward grows from 61 and it goes all the way to 90, 85, 96, and it gets flattened almost at the 87, 88, and it almost reaches the 90 stage here, which it's not clearly visible, but it reached the 90, 95 stage. So you can stop the training at a point where you see that this reward is flattened, and which means after a sustained period, if you see an almost straight line and when you apply the smoothing operation, then you can actually stop the training here. The second most important aspect here is the KL divergence. So KL divergence basically tells you how much the model has deviated while learning from the original model. So if you know the original model is trained on world's knowledge, in a sense, some Wikipedia text or something. So, but if when you're fine tuning the model to learn on a new task, it may sometimes forget the previous learning that it had. So this KL divergence parameter helps us evaluate whether it has actually deviated too much, so that all its pre-training knowledge is lost, also called as catastrophic forgetting or mode collapse, right? So as you can see here, only see occasional spikes. I'll tell you why this is. The bird data set is having very complex schema, and when the weight adjustments happen for those kind of a for the training samples that are coming from the bird data set, you will see that there are occasional spikes, but otherwise the KL divergence is low and this is stable training, and it has not lost any of its original knowledge. Gradient normalization is also an important thing to monitor. You should not see too many spikes, which means the gradients are actually they're just like going way too big or way too small, right? So you'll have to see a consistent pattern. As you can see, there are only occasional spikes here, so I don't see that has impacted the model in a good way. Now, the last thing I want to talk about is the evaluation. As you might have noticed, there are three jobs in the GitHub repository, which I also share in the comment section. So there are three jobs. One is the data preparation job, which you have seen, and there's training and evaluation, which you can run together as a training pipeline. Now, once the model is trained and saved to the underlying data store, you can, in the evaluation stage, we are doing two things. We are again downloading the original base model and calculating a reward function, calculating the reward without any fine tuning. Now, as you can see, for the baseline for the bird data set, the baseline reward is around 59. And for the spider, it's 95. Spider is relatively an easier, is less complex data, has less complex data schema. So, hence the rewards are usually higher than compared to the bird. The average we are making comes to around 71. Now, after fine tuning, we take the fine tuned model. In fact, we download the same model and apply the LoRa weights. And then we again evaluate the model. And this time on the test data set, the same data set we have used for the baseline. And now the test data set is having schema that the model has not seen during the training phase. Now, if you can see the bird the reward average reward for the bird schema has increased from 59 to 70, and for spider it has increased from 95 to 96 because there's only a very less opportunity for them to improve. But however, even 96 is lesser than the GPT 5.1 baseline which we have which I've also done during the beginning of this training. Let's go over this one more time. After running for 5 pokes with 50% of the data and converting 0.48% of the trainable parameters, we notice that the rewards are over the 1390 steps. Rewards climbs from 0.61 to 97, and then they are flattened. The second measure to look for is the KL divergence. Like I mentioned, this represents how much the model deviated from the original model. Too much deviation leads to mode collapse or catastrophic forgetting. In this case, we see that the KL divergence is very minimal. Before fine-tuning, we also calculated the benchmarks of the baseline instruction fine-tuned model on the same dataset. Now, post fine-tuning, we can see a noticeable difference. On spider datasets, we have reached 98, roughly 96%. The reward has increased from 95 to 96, which is 98% of the GPT 5.1 ceiling. That is, like, we have achieved 98% of what GPT 5.1 can do, which is a large language model. Similarly, on the BERT benchmark, we have compared to the baseline non-fine-tuned instruction model. We have noticed a massive gain of 19%, showing that a GRPO training has helped the model learn the complex joints. Like I said earlier, compared to spider datasets, BERT database schemas have more complex joints, and the tables are much larger than the spider data. Now, finally, let's talk about the economics. We started with assuming that there will be 10K calls per day, and if you're running GPT-5 model, we spent around $585 per month. Now, if you take the fine-tuned SLM model running on an A100 GPU virtual machine with scale to 0, it costs around $44 per month. That's roughly 13 times cheaper than the GPT-5 model. However, if you're considering the production setup, you may need always-on model, and it costs around $374, which is 1.6 times cheaper than the GPT-5 cost. This is what makes the SQL text-to-SQL viable at scale. Looking ahead, there are 3 clear next steps that way we can improve this. First is the training on the full spider and the bird corpus. The total number of rows in spider plus bird corpus is roughly around 7,000 rows. So we have only used roughly 1,500 rows, but you can also use the complete 7K rows. It depends upon the appetite of the training. It may take roughly around 20 to 30 hours for the complete training loop. The second thing that we can do is shifting the architecture from you can use Qwen 7 billion parameter model. We could also increase the number of modules that you want to fine tune and see that if the number of if the total reward can reach the GPT 5.1 benchmark. The last thing is the multi-turn loop, where in the model you can use an agentic execution where the model executes, observes the error, and then regenerates. At this point, we're no longer generating the SQL. We are training a system that can think, test, correct itself, and then use the dataset to further improve the SLM outputs. That's the real end game. If you found this helpful, like and subscribe, and let me know what you would like to see next. Thanks for watching.